Okay, Assalamualaikum warahmatullahi wabarakatuh. 2.1 Simple Population Growth Model, Exponential Growth Model. We try to understand the most basic example in mathematical modeling. Background. Mathematical model is applied to understand the population growth dynamics for animal and human populations, for example, fish, bacteria. We try to formulate the changes of population. Is the population increase? Is the population decrease? Or is it fluctuates and so on? Okay, the general compartmental model. The compartmental model is a model that is built using the concept of compartment. In this case, the compartment, we can say that world, the populations depends on the birth, and it will decrease due to death. From the compartment, we try to formulate into words. Okay, the rate of change of population size equal to the rate of birth minus the rate of death. So from the compartmental diagram, we can get this equation. The rate of changes equal to rate of births minus rate of death. We assume that population are sufficiently large so that we can ignore random differences between individuals. Each individual has an equal chance of giving birth and dying. As we know that peoples are different, right? Some can have many children, but some unfortunately not. Okay, but in this model, we assume all people or all animals have the same reproduction rate. Okay, they have equal chance of giving birth and dying. And the second assumption, we assume that birth and death are continuous in time. Next assumption is we assume that per capita birth and death rates are constant in time. Okay, the keyword here is constant. So, for example, in 1990s, we said that everybody averagely can give birth to 4 children, for example, 4 children. But in 2000, average only 2 children. In our model, we assume that whether in 1990 or 2020 or in next future, we still assume that the rate is equal. For example, 3, okay? From 1990 to 2020 is just 3, okay? That is our assumption. And also in the model development, we ignore immigration and emigration, which can be included later. Next, we assume that the at any time is proportional to the size of the population at that time. Rate of change equal to rate of births minus rate of deaths. Okay. Rate of change, we can use x as the variable. The changes of population with respect to time. So we formulate in differential equations. Okay. The name is rate of change. So it is transformed into differential equation dx dt, or students always say derivatives. Okay, derivative dx dt. And rate of birth, kadar kelahiran. We assume that the rate of birth is proportion to the population. So we can put a constant here, beta times x. X is the population. So here. Okay. And then minus, why we have minus here? Because it based on the compartmental model. Okay. The addition to the population is because of birth. Okay. But the population will decrease because of death. So that we need to put minus here. So the rate of death, we put some constant and proportion to the x as well. So we have beta x minus alpha x. Okay. Since we have a similar variable x and x, we can factorize beta minus alpha x. Okay, and we assume that since beta is one constant and alpha is another constant, we can denote r as beta minus alpha. Then our formulation is like this: dx dt equal to rx. So here let x be the population at time t. It is natural to assume that the birth and the death are proportion to the population. This is the stand that we make for this thing. We put beta times x minus alpha times x because we assume that the rate is proportion, berkadar langsung proportion to the population. And the parameter R is called the net growth rate. So we introduce R. Actually, the actual equation is beta minus alpha. Then we factorize, make it R equal to beta minus alpha. And we have to describe what is R mean. What R means? R is called the net growth, also known as growth rate or reproduction rate. Okay, which is the the growth minus the death rate. So if we have R greater than 0, means that the population is growing. And then we have obtained a differential equation for the size for the population xt. Okay, means that dx dt tadilah kita dah dapat dx dt equal to rx. We need one initial condition to ensure a unique solution. Okay, if you see that the equation is not complete, okay, we need initial condition. What is initial condition? We need the information of what is the number of population at the beginning. This is the solutions, how to solve using exact solution. From the differential equation, dx dt is rx with initial condition x naught. The solution is obtained like this: xt equal to x naught ert. Okay? It's very easy to verify this. We use separation of variables. Okay, I will show you 1 over x dx dt equal to r. This is separation of variables where we bring x to the left. Okay, and then you integrate both sides. What is the integration of 1 over x? It is ln x. And what is the integration of r? This will become like this: rt plus c. C is additional constants. And to get x, x is exponent rt plus c. Okay. And then if we assume e to the c is x0, so we can rewrite like this. So we prove that the solution is x0 ert. Clearly, this describes exponential growth or decay. We can have a decay situation if r is negative, right? So it depends on the sign of r. When r 0, the model is exponential growth. It depends on r here. Okay? If r is less than 0, the process is exponential decay. This slide is about exact solution, but we can always try to solve using numerical solution. If we want to learn Matlab, okay, so you can copy all this coding, okay, try, you can do it now. Okay, have you opened your Matlab? Done.
Yes, my Matlab is ready.
Can you copy the coding here?
Yes, I already copy and paste.
Okay.
And then I try to run this code.
Control C. And then you copy that. And then you have to save it first. Okay, save in your computer. Okay, I try to save in the desktop. And then you click run like this. And then it asks whether you want to change your folder. Yes, just answer that. And then it will give you this graph. We can buy Matlab from Shopee. It's only 14 ringgit.
Masih mencuba lagi doktor sebab dia bila
Yang penting kena save dulu. M file tu. Kena save M file. Lepas tu baru boleh run.
Okay, ada yang tanya pasal global K1 tu apa. Alright, so in the Matlab, kita bagi nama function, kita buat dalam function in function. Okay, ini macam nested lah. Kalau you perasan, atas tu function, ni function kan. Bawah ni function lagi. Function yang lain. Okay, macam ni. Global K1. Global K1 maksudnya we define a parameter that can be used in any function. Walaupun kita assume macam ni, function ni rumah lain-lain rumah function 1 adalah rumah 1, function 2 rumah 2. Global, when we set global K1 maksudnya K1 tu boleh digunakan dalam rumah 1 dan rumah 2. Dua-dua rumah boleh guna nilai K1 tu. K1 is, the formulation is dx dt equal to Rx, right? So the R I just changed to K1. Okay, it depends on you. You can use any variable. You can use R as well. But in this example, we use K1. Dx dt equal to Rx. This is the original equation. But in the coding, you can use any variable. It's up to you. For this example, I write K1 is for R actually. Okay, and I set K1 equal to 2. So in the numerical solution, you cannot have unknown value. You have to set everything. Okay? K1 equal to 2, 10 equal to 5. What is 10 equal to 5 means? The graph, the output will be presented along the time from 0 to 5. If you want to see the behavior at time equal to 10 or time equal to 1000, you just can change this value. X0. X0 is the initial value of the population. In this example, 10 to the power of 5. Okay, even you see that this is like 0, but you have to see the scale here is time 10 to the power of 9. Okay, so sebenarnya ada nilai kat sini, bukan kosong sebab dia kecil sangat berbanding 10 kuasa 9. Kita nampak dia macam kosong, tapi sebenarnya nilai dia adalah 10 kuasa 5. And then what is these lines means? T sol, X sol equal to ODE 45. Okay, this is the advantage of Matlab. ODE 45 run the method of range quota. This is numerical method. So you can just call the library of ODE 45, it will run range quota. What function it will compute? ODE 45 at RHS. This is another function. As I said, rumah nombor 2, ini adalah different function. So dia akan call ke sini, RHS. So what is RHS function? It takes global K1 because they want to use the same value of K1. So it's easy to just write global K1. And X dot is this, dx dt. K1 times X is the formulation for R times X.
Where do you get the ODE 45? We need to key in first to the Matlab, or it's already built in the Matlab?
It's already built, yes. It's already built in Matlab. ODE.
So we just call them?
Yeah, you just call the library and it will run that for you.
So how do you know the command to call them?
The command is ODE 45. You put bracket and put the function that you want to call, put the timeline and put the initial value. If we see that the behavior is exponentially growth, look at the curve. Okay, this is the behavior of exponential. So it consistent with our exact solution. Exact solution kita pun dah tahu exponential kan. Bila kita buat numerical pun memang exponential dah terbukti dah dalam coding ni, dalam output dari coding Matlab ni. Solutions over time. Using the model, we can predict the time taken for the population size to double, for example. Okay, class. If we have this model, and you can simulate not only, for example, not only 5 years, you can formulate until 1,000 years. What will happen after 1,000 years? Okay, you just put the value into the coding and you can see the behavior, it will increase exponentially. So that's the advantage of using model. Without actually, we are at that moment, okay, we can predict what will happen in the future. Okay, that is the simulation study. Okay, the keyword is predict. Okay, the model can predict the time. For example, you want to know when the population size to double. If the population now is 5, when the population will be 5,000, for example, 5,000. When the population will be 10,000, is it 2 more years or 3 more years, and so on. Okay, we will know the estimated value. Okay, what this model predicts for known values of the parameters, for example, r equal to 0.017. So in the coding, you can change any value. Try put lower value of r. For example, from 2 just now. What will happen if the rate is less than 2, for example, 0.017, what will happen to the behavior? Okay, so that is the simulation study. And we can change the initial values, and you can predict the population after 5 years, 10 years, and 100 years. Okay, the other important part is model validation. You can validate by compare the prediction with population size at previous time for which data are available. As an example, okay, in this project, okay, the data, the behavior like this, okay, you can see the dot is data. But if you use the model, which is exponentially increasing, it just match the data at the beginning, okay, but not at the later stage of the time. Okay, you can see that this is very big gap. That means the model did not predict well. But we can always, if you do the modeling, you can always have justification. Okay, so we can say situation 1. The prediction appear to get worse the further back we go. Okay, for example, the prediction is good for 2020. It can predict very well. Okay, but when you test the same model to the earlier time, for example, is in 1800, okay, the model cannot predict it well. Okay, it's not matched. Okay, so why? Okay, we need to answer why it happens. Okay, one possible contributing factors to this discrepancy is that the birth and death rate have changed gradually due to improvements in technology and changing attitudes. For example, in 2020, the rate is, for example, 1.5. But in 1800, maybe the rate is different. Maybe the rate of growth is just 0.9. Okay, that's why there is a big discrepancy for the year for the back. Okay, so that is the reason we need to justify. We need to give the meaning, the physical meaning. Okay, sometimes we face the other situation. The model appears to be in good agreement in the earlier stages, like in this result. Okay, why? but for later times the population level out rather than continuing to grow exponentially. Why? We can give the reason. The cause of this, that the death rate increases due to the crowding and competition. So we have to fix the model, means that the model is not accurate. We need to consider the other factor. The death rate is not only because of the natural death. Maybe it's due to the competing factor. Apa, bersaing sesama sendiri. Kalau animal tu kan, mungkin limited resource, mungkin makanan tak cukup kat kawasan tu. There is always another factor. Okay? In certain animal population, the birth rate decreases when the death rate increases. So, dalam situasi lain, mungkin ada animals yang birth rate decrease when the death rate increase. Another reason, the growth rate is treated as a constant, is only valid local in time. Ini maksud macam yang atas ni. Okay. So, dia kata kat sini, sebenarnya R should be time-dependent parameter. It cannot be constant. Okay, so yeah, that is the mathematical modeling. Somehow we can predict well, but somehow we can't predict, but we have justification. We need to understand why it happens. Okay, so there is a need to extend the model. There are several ways in which the basic population model could be extended. For example, we put another factor, incorporate immigration, emigration factor, others than that, harvesting in the population or competition or limited resource and so on.